Good day, grade 12 learners and teachers. Welcome to today's mathematics lesson. My name is Sibusiso Towe. This lesson is brought to you by the Gauteng Department of Education in collaboration with Cybono Discovery Center. Right, good people, today we are going to be looking at the revision of paper 1 concepts that you'll be writing on tomorrow. Remember, with the time that we have, it is impossible for us to can do everything. So we selected two heavily weighted topics that would be differential calculus as well as functions and inverses. Those are the two focus topics that we'll look at today. The rest of the topics, we believe that you can practice and ensure that you are ready for the big one tomorrow. That should be the first examination this year in grade 12. And we hope that you are going to prepare yourselves thoroughly. Right now, we're just trying to iron out a few of the concepts that you might have problems with. Remember, we also have our WhatsApp interactive number 064748 8913. That is 0647488913. You can use that number to ask questions based on today's lesson, and the number will keep popping up at the bottom of your screen. Right. Let's first look at the mark distribution as well as target setting. The mark distribution for the paper that you'll be writing tomorrow, for algebra, you should be expecting 22 to 28 marks, and you should check it on, mostly it should be on question 1, and then we look at patterns and sequences. The marks would range between 22 and 28. Possibilities are that it would be in question 2 as well as question 3. And then our focus topic for today, you can see it's highlighted in green, that is functions. It is weighing between 32 to 38 marks, and you can find it in question 4, question 5, and question 6. Remember, your functions will encompass grade 11 concepts as well as your inverse functions. And then you have finance, the grade 11 finance that you did last year. It is also examinable between 12 to 18 marks, so you should look out for that as well. Possibilities are that you might find the question in question 7. And then we have our other focus topic for today, that is differential calculus, ranging between 32 to 38 marks, and you can find that in question 8, 9, and 10. And then you'll have probability as well, which is also a revision of grade 11 concepts. So you'd expect that to weigh between 12 to 18 marks, and we'll find that in question 11. Now, if you look at the two highlighted topics, you can see their weightings. They are very heavily weighted. Functions and calculus, they make a bulk of your examination. They make about half of the exam paper. So you need to ensure that you've ironed out all the problems that you might be having on those concepts. So those are the two concepts that we look at. Now, in terms of minimum targeted marks, these are the marks that you should be targeting per topic in order for you to just get a minimum pass. But remember, if you want to get a bachelor pass, then you should be targeting the marks that I've highlighted here, and then which means that you might be in a position of getting 94 marks if you are able to reach those targets. Obviously, good people, you know, if you are targeting a distinction, then you should obviously be getting more marks than what we've actually written here. So our focus here was just on the minimum marks for you just to get a pass. These are the marks that you should be targeting, and then the marks to get a bachelor as well, they are indicated there. Right, let's start. Obviously, you'll always be given an information sheet. It is of paramount importance that you know how to use it. So please ensure that you familiarize yourself with the information sheet, and you use it in your test, you use it in your classworks, so that you get to familiarize yourself with where specific formulas are. Right. Obviously, because we are dealing with calculus, we'll focus mostly on this one. This would be the definition, and also quadratic equation, obviously we cannot leave that out because we'll be solving a lot of quadratic equations there. And then from there, obviously, we're also looking at the concept of functions, so we might be focusing on these formulas. But you should remember that at times they integrate some paper 1 work with paper 2, so you should be able to also cope with those integrative questions. Right, they continue. This part is mostly used in paper 2. That's what you'll be focusing on as you prepare for paper 2. And then let's start with our functions and inverses. We look at those examined concepts. Obviously, we should be able to sketch all algebraic functions in the form y is equals to ax plus q. That would be your linear function. That would be your linear function. And then you have also y is equals to ax squared plus bx plus c. That should be a quadratic function or a parabola. Quadratic function. Remember, it can also be given in the form y is equals to a into x plus p squared plus q. Can also be given in the turning point form rather than being given the Joule-intercept form. And then we also have what we call the rectangular hyperbola. The hyperbola. So you should also be able to sketch that and also interpret. We also have our exponential function there, Right. We should also be able to sketch the inverse functions. We will go to that. You'll see the standard forms there. You should be able to determine the domain, the range, the asymptotes, turning point, intercepts, lines of symmetry, increasing and decreasing function of each of these functions. And you should be able to interpret. Remember, with interpretations come a lot of other concepts that you need to know. Inequalities with functions, determining the horizontal distance, the vertical distance, nature of roots, transformation. So those are the things that pop up when you start doing your interpretation. Please make sure that you are well vested with the knowledge that you should have for those specific concepts. Right. Now, let us quickly look at the properties of a linear function. We're just going to look at the standard properties quickly. The standard form obviously takes y is equals to mx plus c, or y is equals to ax plus q. And then now we are going to be looking at the gradient itself. The gradient, the value of a or m that represents the gradient. If the gradient is positive, then we have what we call now our increasing function. Would have this function here, the increasing function, to say when the values of x increase, the values of y also decrease. So they made an error here. This line was supposed to be here, and this one was supposed to be there. So I'll just redraw that one for the decreasing function. So this one shows that as the values of x increase from left to right, as the values of x increase from left to right, the values of y are decreasing. So it's a decreasing linear function. And then the domain, x an element of all real numbers if there are no restrictions on the function, and the range, y an element of all real numbers if there are no restrictions there. Obviously, there is no turning point, there is no asymptote, there is no axis of symmetry for the linear function. Right, we move on to the rectangular hyperbola, the hyperbolic function. The standard form is y is equals to a over x plus p plus q. Remember, in grade 10, when you look at this function, you looked at it in the form y is equals to a over x. That would be the most standard form before it was translated. In grade 10, you said you look at the mother function and then you look at the vertical translation plus q, where you move the graph up and down. So where the standard form comes from. Now, it's a decreasing function if a is greater than 0. It's a decreasing function, and it will be located within the first and the third quadrant of the asymptotes there. And then from there, decreasing function when a is less than 0. Remember, that is the parameter a. It is telling us about the location of the the arms of that particular function. You can see here it's the first quadrant as well as the third quadrant, but now if it's a decreasing function, it's an increasing function, it's the second quadrant as well as the fourth quadrant. So now you can see from, if you look at the graph from left to right, if you look at the a greater than 0 from left to right, let me just draw a sketch there. If you look at this graph from left to right, you can see as the values of x increase from left to right, the values of y continuously decrease. Also, if you look at this arm, as the values of x increase here, the values of y continuously decrease. So we refer to this as the decreasing function. And also this one, when you read it from left to right, you can see as the values of x gradually increase, the values of y are also increasing. So you refer to it as the increasing function. Now with the domain, the graph is defined for all real numbers except at the asymptote, because the graph is not allowed to touch the asymptote. Remember, by definition, an asymptote is a line where the graph will not be defined. So the graph will move very closely to the asymptote, but it will not touch the asymptote, because at the asymptote it is not defined. So the graph will be defined for all real values of x except for the asymptote. For the range, the graph will be defined for all real values of y except for the asymptote as well. There is no turning point. That's very important. There is a vertical asymptote, that is x equals to negative p. There is a horizontal asymptote, y is equals to q. And then there's axis of symmetry. To determine the axis of symmetry, you can use this equation. This would work for the one with a positive gradient, and this one would work for the one with a negative gradient. Remember, there are so many methods that one can use to determine the equation of the axis of symmetry. Other educators would approach it using y is equals to mx plus c, where x and y represent what? They represent the point of intersection. Point of intersection of the asymptotes. So that's another way of doing it. They would use, sorry for that, y is equals to x plus c for the positive gradient, and y is equals to negative x plus c for the one with the negative gradient. Remember, the point x and y represent our point of intersection of those asymptotes. So this is another way of doing it. This is another one, another method of doing it. So you will stick to the method that you were actually taught. Right. Let's look at the quadratic function now. Second degree function. I did actually mention this standard forms. This would be the turning point form, and this would be the dual intercept form. Now, if a is greater than 0, the graph is said to be concave up. We normally say it has a smiling shape. And then if a is less than 0, it's a mistake here. A is less than 0, the graph should be concave down. The graph should be concave down, or what we normally refer to as the set face. But the mathematical terminology to use is concave up as well as a concave down. Now, the domain x takes an element of all real numbers. The graph is defined for all real values of x. And now when it comes to the range, the graph is defined. I'll give an example. Suppose that you have the second degree function that is sketched for you, and then you have that this is the maxima. This is the maximum point that the graph reaches. Let's say that it has a maximum point of 1 and 8, for argument's sake. So this graph is only defined at or below the turning point. That is for the range. It's defined at or below the turning point. So the range of this one would be y, an element of all real numbers, but y should be less than or equals to what? Equals to 8. So that would be the range of the function. So now we try to explain it here, that it would be y is greater than Q if A is greater than 0. So if you have that the graph is concave up, then the graph should be defined above the y value of the turning point. That is why we are talking to y greater or equals to q. Here, that is why we are talking to y greater or equals to f of minus b over 2a. F of minus b over 2a is the y value of the turning point. This is the y value of the turning point. So it will be defined above that. But if it is concave down, then it is defined below the turning point. At or below the turning point, that's where the graph is defined. But if it is concave up, it is defined at or above the turning point. That is why here we are saying it has reached a maximum, so it is defined at or below that maximum value. And then this one, because it has a minimum, it is defined at or above the minimum. So that would be the range of the function. That's where the function is defined. So the graph, most importantly, it has no asymptote. It has what we refer to as the axis of symmetry. To work it out, we use x is equals to minus b over 2a. Remember, the axis of symmetry is the line that divides the graph into two equal halves. Remember, do not confuse axis of symmetry with the asymptote. The asymptote is a line where the graph is not defined. It approaches that line, but it will not touch that line because it is not defined on that particular line. But when we talk about axis of symmetry, it's the line that would divide the graph into two equal halves, right? We move on. We look at the exponential function. Obviously here, the parameters a, b, and q are going to actually speak volume about what happens to the standard exponential function. Remember, the standard exponential function there would be given by y is equals to a to the x. So now we have to then look at those parameters there. Now, the parameter b, if it's greater than 1, it is said that the graph would be above the asymptote. If you have the asymptotic line here, the graph should be drawn above the asymptote. But if b is less than, if b is trapped between 0 and 1, so we look at the shape as well as the position. If b is greater than 1, then we have that it is and a is greater than 0, it's above the asymptote. So a tells you whether you are above or below the asymptote. So if a is greater than 0, you are above the asymptote. If a is less than 0, the graph will be drawn below the asymptote. Now, both the value of a and the value of b are going to give us the shape as well as the orientation. If b is trapped between 0 and 1, values that are trapped between 0 and 1 can be half, can be 1 over 4. These are values that we can use for b. Those are values that are trapped between 0 and 1. So it says that if a is greater than 0, and b is trapped between 0 and 1, we find that this becomes a decreasing function. This one, you can see that now this is an increasing function, this one is a decreasing function. Now, if b is greater than 1 and a is less than 0, yes, it's below the asymptote, but it is also a decreasing function, this one. But now, if b is trapped between 0 and 1 and a is less than 0, yes, the function is below the asymptote, but it is now an increasing function. So those are the things we should be looking out for. The domain, the graph is defined for all real values of x, but the range, the graph is defined above the asymptote if a is greater than 0, and it is defined below the asymptote if a is less than 0. I'll give an example. Let's say that the asymptote is this line, y is equals to 2, and then we've sketched our exponential function there. The range of this function would be, the graph, remember, it's not defined on the asymptotic line, so the graph should be defined above, so y should be greater than 2. Y should be greater than 2. If A is positive, if the graph is located above the asymptote, then we get that it is defined above that asymptote. But if you have something like this, let's say Y is -3, that's the asymptote, and you get that the graph is sketched here like that. So we will say that now with the range of this one, Y should be less than -3. This graph is defined below the asymptote if A is less than 0. Right, there's actually no turning point for this function, and the asymptote Y is equals to Q, there's no vertical asymptote. It only has that horizontal asymptote, and there is no axis of symmetry. No line can be drawn in this function and cut the function exactly in 2 equal halves, so we do not have an axis of symmetry. Right, now let's look at the inverse functions. Now these are the 3 standard forms of the inverses that you are required to know. Y is equals to ax plus q, y is equals to ax squared plus, just ax squared, and y is equals to b to the x, where b is greater than 0 and b cannot be equals to 1. Remember, when you look at this one, you should also remember the restriction of the domain. The restriction of the domain to make f a function, to make y equals to ax squared a function, or to make the inverse, the inverse of y is equals to ax squared a function, because the inverse of this function, if you are to draw just as an example, you have y is equals to x squared. This would be the function. This function, when you look at it and you subject it to a vertical line test, you can see that the vertical line intersects the graph once, which means that this graph is a function because it is a one-to-one mapping. Now, if you are to draw the inverse of this function, you see now that sketching the inverse of this function, you get to the function like this. And if you subject that to a vertical line test, the vertical line now intersects the graph in 2 different positions. So which means that now this is no longer a function. So we can then restrict the domain to make it a function. Please ensure that you revise those important concepts. Now, the inverse, by definition, is a reflection about the line y is equals to x. So if someone says determine the inverse of this particular function, the first step would be to interchange x and y, because it is a reflection about the line y is equals to x. To determine the inverse, swap x and y. E.g., you have y is equals to 2x minus 3. You can see now, instead of y, we put x. In the place of x, we put y. And then we make y the subject. That is what we obtain there. So this would be the inverse of f, because this is now the function f. This would be the inverse. So to get that inverse, we need to interchange or to swap x and y like that. Right, we move on. Now, we can also look at the graphical transformations here. Remember, the 2 important aspects of the transformation. You are reflecting about the x-axis and you are reflecting about the y-axis. Remember, you can also translate vertically and translate horizontally. If you reflect about the x-axis, then y becomes negative. If you reflect about the y-axis, then x becomes negative. That's very, very important. Now, reflection about the x-axis, or the line y is equals to 0. If you reflect about the x-axis, a point 2 maps -3. We said here, when you reflect about the x-axis, y becomes negative. So you can see here that this point 2 maps -3 became a point. Now you leave x as it is, but y becomes negative, so -3, and then this becomes a point 2 maps 3. That is how you got the new point, because you multiplied the y values by -1. So now let's look at what happens in the function itself. You can see that there's y is equals to 2x squared. Now, because you are reflecting about the x-axis, y changes and becomes -y. So you can see that y was now replaced by -y, and we made y the subject. So that is how we reflect about the x-axis in the function. Right, let's look at the reflection about the y-axis. If you reflect about the y-axis, then x becomes what? -x. So now you can see here we have y is equals to 3 to the x plus 1, and then now x is replaced by -x to obtain a new function. That is the transformation of the original given function there. Right, good people, that was just the summary of the concepts that you needed to look at as far as functions are concerned. Now let's go to problem solving and interpret a few of these functions. Right, given k of x is equals to a over x plus p plus q, R to map 3 is a point of intersection of the asymptote. That's very, very important. It is the point of intersection of the asymptote. So you can see that point R here, that's where the asymptote intersect. So if they give you the point of intersection of the asymptote, they are indirectly giving you the asymptote, because if R is the point of intersection 2, 3 of the asymptote, and from the original function, we know that the asymptote, the vertical asymptote would be x equals to -p, and the horizontal asymptote would be y is equals to q. So now it means that if you are given point R is in the form minus p and q. So they are indirectly giving you the values of the asymptote. Now, write down the equations of the asymptote. So fortunately, that's the first question that they are asking us. I think we've already responded to that question indirectly. Let's see. Now you have that x is equals to 2, because you are given there at point R that x is equals to 2. So that would be your vertical asymptote. X is equals to 2. Now let's look at the horizontal asymptote. The horizontal asymptote obviously would be given by that y value there. Y is equals to 3. So that would be the horizontal and the vertical asymptote. They are defined by both x and y. Please remember, good people, when they want equations of the asymptote, do not write down the value of p and q. Write down the x value as well as the y value of the asymptote. If they are looking for p and q, they are going to specifically ask you to write down the values of p and q. If they say write down the value of the asymptotes, please write them in the form of x equals to or y equals to as well. Right. Now, let us look at the second question. Now they are actually asking us for those parameters a, p, and q. Remember, we already have the horizontal asymptote, we have the vertical asymptote. So if we have those, it means that we have p and we have q like that. So we are left with the value of a. So for us to calculate the value of a, we need an additional point on the function, and fortunately we are given point q. Remember, to determine the equation of any function, you are going to need a few parameters from the function. In this case, it's a hyperbolic function. You are going to need the asymptote as well as an additional point that would allow you to calculate the value of a. Now let's check here. That is the standard form. Now y is equals to 3, which means that q is equals to 3. We are taking it from what? We are taking it from the vertical asymptote. We are taking it from the horizontal asymptote, that y is equals to 3. So q would be 3. Now let's look at now the other asymptote. X is equals to 2. We have that x is equals to 2, that vertical asymptote, and then it means that p would be equals to -2. Remember, y or q is equals to 3. This represents your, or y is equals to 3 here. This represents your asymptote. In this case, it will represent your horizontal asymptote, and this one would represent your vertical asymptote. So you've already worked them out, which means you can get the value of P as well as the value of Q. Now, I told you, if you want the value of A, you need both those asymptotes and an additional point. Fortunately, we are given a point Q, which has 1 and 0. So now, if you are to substitute point Q on the original function as well as the value of PQ, we substituted the value of P and the value of Q and the point on the graph. This is the point on the graph there. So now that allows us to calculate A, and we get that the value of A is equals to 3. Now we've calculated A, P, and Q. So we've answered that particular question. Right. Let's move on. The coordinates of S. Now let's look at point S. Remember, you've worked out the value of A, the value of P, and the value of Q, which means you now have the equation of this rectangular hyperbola. Now, we are looking for the coordinates of S. And you can see that here, point S lies on the y-axis. It lies on the y-axis, which implies that point S is a y-intercept of F. If it is a y-intercept of F, how do you work out the y-intercept? You put x to be equals to 0. Now let's see here. Obviously, you can see from the equation, we substituted x with 0 because point S is a y-intercept. And for y-intercept, x equals 0. That is where this 0 comes from. Right, and then from there we solve, we get that y is equals to 3 over 2. So we've simplified, we got y is equals to 3 over 2. So which means that the coordinates of S now, therefore, the coordinates of S would be when x is 0, y is equals to 3 over 2, like that. So those are the coordinates of point S. Right. We move on. Write down the domain of K. So we want to write down the domain of this function. Remember, when we were still doing our review, we said the domain of a hyperbolic function is all real values of x except the asymptote, because the asymptote is where the graph is not defined. So the graph is defined for all values of x except for the asymptote. Now let's check here. Obviously, we indicated x an element of all real numbers, but x cannot be equals to 2 because 2 is the horizontal, or rather the vertical asymptote. So it is not defined on that vertical asymptote. It's defined on the whole number system, but not at the asymptote. One can also write it like this if one is using the interval notation. One can say x is an element of all of numbers from minus infinity to 2. So you are now talking to this arm to say it's defined for x is negative infinity up until we are stopped by the asymptote 2, but it is also defined just above 2. So it is also defined from 2 to positive infinity. Now you are referring to this arm here, that the positive infinity here, and then defined at just above 2 to positive infinity, or just below 2 to negative infinity. So you can also write the domain that way. Depends on how you were actually taught. Right. Now we've just completed the example on the linear of the hyperbolic function. Now we move on to a parabolic function. Now we move on to a parabolic function. The sketch below shows the graph of g of x is negative 12x plus 12. So we have that the parabola and a straight line are drawn on the same set of axes. A and B are the x-intercepts of f, and C is a point on f. D is a point on G, such that CD is parallel to the y-axis. H and K are the points of intersection of F and G. Determine the length of AB. Good people, I think this one, you can be able to do it. Let me just give you just 3 minutes. Let me give you 3 minutes for you to quickly do this one. Determine the length of AB from that particular parabola there. So I'm just giving you a quick 3 minutes to just work it out, and then we'll come back and look at it together. Your 3 minutes time starts now. Hello and welcome back, good people. Right, let's look at this question. I hope that you were able to work it out. It's not a difficult or a higher order question. It's just a basic question. They're looking for the length of AB. So the length of AB, this is what we are looking for there. That's what we are looking for. So we are going to be looking at points A and B. You can see that points A and B are points on the x-axis. So these are x-intercept. This is the x-intercept of F. This is also the x-intercept of F. Now, how do we determine the x-intercept? We are going to equate y to 0. and solve for x. So that's what we should be doing. And then from there, after we've worked that out, we can see that the length of AB is a horizontal length. So to determine the horizontal length AB, we are going to take x on the left, take away x on the, no, we should be taking, for AB, we should be taking the x value on the right, subtract the x value on the left. So we would be having x at B, subtract x at A. That would give us the length of AB after we've determined the value, what you call the x-intercept, and the value at A and the value at B there. So now, that's what we're going to do. That's the first thing. We are going to equate y to 0. That's how we find the x-intercept. Now, after doing that, we divide that by -3. We've divided everything by -3. -3 divided by -3, x squared, we are left with x squared. -9x divided by -3, we get plus 3x. +30 divided by -3, we get -10. So to factorize that, we will have the factors x plus 5, x minus 2 equals to 0. And then from there, x is equals to -5 or x is equals to 2. These are our roots. So we know that this one would be -5 and this one would be 2. So to calculate AB, we'll take x on the right, that is x at B, that is 2, take away -5. So that should be 7 units like that. Let's just confirm here. Let's just confirm. Yes, indeed, AB is equals to 7 units because it's a horizontal length. So we take the x value on the right, take away the x value on the left. Right. And now we are looking for the coordinates of K. Let's locate point K. Now, remember, good people, when they want the coordinate of any specific point, you check where that point is with respect to the function. Please make sure you check. We wanted, the first question, we wanted the length of AB. So we checked where point A was on the function and where point B was on the function. And we found that for us to determine the x-intercept, we put y to be equals to 0, then we solve. But now, when you look at point K, you can see that point K is a point of intersection. That is where the two graphs are meeting. So point K is a point of intersection of F and G. And remember, points of intersections are where the graph share a common point. So you say that the graph of F is exactly equals to the graph. The y values are exactly the same, as well as the x values are exactly the same. But if you are given y as a function of x and y as a function of x, we can then equate the y values in order to find the corresponding x values on those particular points. So we are saying this is a point of intersection. How do we determine the point of intersection of the function? We equate f of x to g of x because they have the same y values and the same x values. In this case, y was made the subject, so that is why we equate the y values there. So that is the most important takeaway from that. So you can see here that we've equated f of x to g of x. That's what we've done there. So equating f of x to g of x and then writing it in standard form by making sure that we then transpose the 12x and the 12. So when we simplify, we get that -3x squared plus 3x plus 18. From here, you can see 3 is common, so we can divide uniformly throughout by -3. If we do that, we get x squared minus x minus 6 equals to 0. That is in standard form, so we can actually here be in a position of factorizing this either by means of inspection, or we can use the quadratic formula to just work out the roots. But remember, if it is factorizable by inspection, then we should factorize by inspection. So we would get that this should be, if we factorize this, it should be x and x equals to 0. And then we have that the factors of 6 would be 3 and 2, minus and plus. So those are going to be the factors which will ultimately lead us to those roots there. So now that we've found the values of x where the graphs intersect, we then need to check. Remember, the graphs intersect here as well as there. So we found the two values of x where the graphs intersect. The two values of x, negative 2 and 3, you can see at h would be using negative 2 because the x value at h is negative, the x value at point h is negative, but the x value at point k is positive. And we got two values, one negative and one positive. So we'd say that here we have the 3. So because we are looking for the coordinates of k and we took only 3 as the value of x on that particular point, then we should be substituting it in either f of x or g of x to get the corresponding y value. Now if you check here, at k, x is positive. That is why we chose what? We chose 3 because at k, the x values are positive. So if you substitute 3 in the linear function, you get negative 24. So we get that the coordinates of k should be 3 and negative 24, like that. So that's how we actually work out the coordinates of the point of intersection there. There we go. Those are the coordinates of k there. Right. Let's move on. Determine the values of x for which f of x minus g of x is less than or equals to 0. Now, if you look at this, now, f of x minus g of x is less than or equals to 0. First thing that we should do, because we do not have a number less than or greater than 0, we have exactly 0. We can just transpose the g of x or determine the additive inverse of that g. So this would be f of x less than or equals to g of x. Now this speaks to us. It says to us where we want a region where graph of f is equal to or less than the graph of g, where the y values of the graph of f are equal or less than the y values of the graph of g. So we want where f is below. But first things first, for us to know where it is below and where it is above, we need to locate the point where they are equal. And that would be our point of intersection. We've already worked out here that we have negative 2, and we've worked out here that we have 3. That's what we worked out in the previous slide. Now, we are going to be drawing our vertical lines here on these points of intersection, and then we are going to be looking at a region. We are going to be checking. Remember, our critical values negative 2 and 3, and the values are included. We are going to be checking on the left-hand side of negative 2. We're going to be checking the graphs here on this portion, on this side, on the left-hand side of the first point of intersection. You can see here that it is G that is above and F is below, and here they are looking at where F is below. So you can see that indeed it is through this side. It is through this side on the left hand side. G is indeed above and F is below. Now let's look at the region in between the two. Let's look at this region, the region in between the 2 points of intersection. Now if you check here, you can see that this is the graph of F and this is the graph of G. You can see that the graph of F, the parabola, is now above, and that's not where we want our answers. We want our answers where the graph of F is less than. So we are looking at F below or equal to G. F is below or equals to G. So at 2 they are equal, and at 3 they are equal. And at less than negative 2, you can see that indeed the condition is met. Now let's check after the point of intersection. You can see that here again G is above and F is below. So we meet the condition there. So we are meeting the condition here as well as there. So that's where our answer lies. Now, let's check here. Obviously, that's the first thing that we did. We said, let us transpose the g of x so that f of x is less than g of x. And then we can see that it is where x is less than negative 2, as I indicated here, as I indicated there, or when x is greater or equals to 3. That is where the condition that they are looking for is met, where the y values of f are below or less than the y values of g, or equals to them. Or we can say where f is below g. F is below or equals to g, where the graph of f is below or exactly the same as the graph of g. Right. Now, let us look at the next question. Determine the maximum length of CD. CD. Now, if you look at the length of CD, it is the vertical length. And if you are looking at the vertical length, obviously you should be taking the y value at the top, take away the y value at the bottom. So if you are looking for CD, you should be taking y top minus y bottom. Now, in this case, when you look at these two functions, we are not given the value of y at C. So this should be y at C minus y at D. You are not given the value of y at C, you are not given the value of y at D. So we are going to be taking the equation of y at C, that is f of x, minus the equation of y at D, that is g of x. So from there, we will get the expression for CD, and then we will maximize it. Now, let's check that one. You see, that's the first thing that we did. We said CD is f of x minus g of x. That is y top minus y bottom. Right. The top equation minus bottom equation, because we are not given those individual values of y. So now we get this expression, which we can obviously simplify. If we simplify that, we can distribute the negative, we get plus 12x minus 12. And then if we simplify that, we get negative 3x squared plus 3x plus 18. So this is the expression of CD. This is an expression, that gives us the relationship between length CD and the values of x. So it is telling us the length of CD as the values of x are actually changing. Now, if we want the maximum length. So if we want the maximum length, remember, good people, we can actually differentiate CD and get the value of x where CD is a maximum. Or we can use the completion of the square to get the maximum value directly. Or we can use x equals to minus b over 2a to determine the value of x where CD is a maximum, because this is actually parabolic, because it's 3x squared plus 3x plus 18. So it is in the form ax squared plus bx plus c. So we can use any of those three methods. Now, checking this out, we use the CD, the x. So we are using calculus here to get the value of x, and we know that the maximum is obtained when the derivative is equals to 0. So solving for x, we get that x is equals to half is the value of x that would give us the maximum length. So this is the value of x that will give us the maximum length of CD. So now we have to go back and substitute it in the original expression for CD. So when we substitute it in the original expression, where we see x, we put half in this expression. And then from there, you can see that the maximum length is 75 over 4 or 18 and 3 over 4 units. So that would be our maximum length of CD. Remember, CD is a vertical distance. So what is important is we take y top minus y bottom. And then from there, we determine the value of x by either using the completion of the square, x equals minus b over 2a. Those are the concepts that you learned in grade 11, but this year you've already also learned that you can maximize using calculus, the derivative. So we worked out the derivative of CD with respect to x. We equated it to 0. We determined the value of x that gives us the maximum length of CD. Then we substituted back in the original equation, and then from there we worked out the maximum length of CD. Right. We move on now to another interesting one. This one is the integration of the nature of roots with the functions. So they are saying for which values of p will f of x equal p have a positive and a negative root, one positive and one negative root. So now, if you look at this f of x equals p, we are looking at a line y is equals to p. So they are asking us to move a line y is equals to p, a line y is equals to p with respect to the function. We want to move this line up and down with respect to our function, but we want to locate a point where, or a region where if we move this line, we are going to get one positive root and one negative root. So where should our horizontal line be located? In which point or in which region should it be located such that the graph cuts the x-axis on one point, on one point on the negative x-axis, and also on one point on the positive x-axis. So now I've drawn this line that we need to use. So we are going to be testing now which point or which points or the region that the line should be moving in order for us to get what? One positive and one negative root. Now, if you look at this now, if you look at the y-intercept, the y-intercept is y equals to 30. If you are to move this line just below the y-intercept, like that, you can see you are continuously touching the graph on the positive x-axis and the negative x-axis. But look at the line that I'm about to draw now. You see, this line that I just drew, you are intersecting the graph on two x values that are both negative, and the examiner was clear here, one positive and one negative. So below that y-intercept, you can see everywhere below the y-intercept that indeed I am intersecting the graph on one positive x-axis and one negative x-axis. Even if you can draw your line here, you can see you are intersecting on the positive x-axis and also on the negative x-axis when you look at where the line itself intersects the parabolic function. So we say that it is where p is less than 30 because y is equals to 30. Y is equals to 30 is our y-intercept. All the points below the y-intercept, the condition is met. So when the line is moving below the y-intercept, we see that it is intersecting on the positive x-axis and also on the negative x-axis. And that's what the examiner is actually asking for. Let us look at that illustration there. You can see now, you can see if I put in that illustration, you can see as the line moves below the y-intercept, you can see as the line moves below the y-intercept there, again, you can see as the line moves below the y-intercept, it is intersecting on the positive x-axis and the negative x-axis. So that's where P is less than 30. So that is a question of a high order, but it's not that complex. You need to understand this nature of roots. Right. We are moving on. Right now we get to the inverse functions. The inverse function. So we are looking at an example of an exponential function and as well as its inverse. So the graph of g of x is equals to a to the exponent of x is drawn in the sketch below. The point S, which is 2 and 9, lies on g. T is the y-intercept of g. Is g an increasing or a decreasing function? Right, if you look at the graph from left to right, good people, you can see as the values of x from left to right, as the values of x increase, the values of y are also increasing. So we see that as the values of x on the graph, can see the values of x are increasing from negative to positive. You can see also the values of y are also increasing. So we say that it is an increasing function. Let's see. Indeed, g is an increasing function because when the values of x increase, the values of y also increase. Now, we are required to calculate the value of a. In order for us to calculate the value of a, what we can do is we have y is equals to a to the exponent of x. So, and we are given a point 2 and 9. We can substitute x for 2 and y equals 9. Then we calculate the value of x. Let's see. Where we see x, we put 2, and where we see y, we put 9. That's what we just did. And then from there, we simplify. We get that a is 3 because now a is positive. The value of a is positive. It can never be negative. That is the restriction there for the exponential function. Right, so because a is positive, so we get that a is equals to 3 like that. So now, the next question, determine f inverse in the form of y equals to. So we need the inverse of that function. Remember, we've just determined the value of a, and we got that the value of a is 3, which means y is equals to 3 to the x. So in order for us to determine the inverse, we need to interchange x and y. We've already spoken about that. Interchange x and y, and then after that, we can therefore write y as the subject of the equation. So now let's check. If we interchange x and y, we can see x will then be equals to 3 to the y. And then from there, if we want to write this in, to write y as the subject of the formula, because this is exponential, we are going to be using logs. So we are going to stick to the log of a number to its base is equals to the exponent. So we are going to write this in exponential or in log form, so as to make y the subject of the equation like that. Now they say write down the equation of the asymptote of g of x minus 5. So what do you notice about this g of x minus 5? We are taking the graph of g and we are subtracting 5 from it, which means that we are moving it vertically by 5 units downwards. So we are saying now g is translated 5 units down, which means that the original asymptote, if you look at the original function, what was the asymptote? The equation of the asymptote of the original function, it was y equals to 0. So if the graph is shifted 5 units down, it means that the asymptote will also shift 5 units down. So it would be 5 units shifted, so y would be -5 like that. So let us just verify that one. Indeed, y is equals to -5 because you are shifting the graph 5 units down, which means the asymptote, the original asymptote, which was y equals to 0, will also be shifted down, because what you are going to get now is that the graph will now have an asymptote like this. It will now shift y is equals to -5, like that. It will now shift 5 units down. So the asymptote, or all the points, are going to shift by 5 units downwards. Right, we move on. The graph, or rather, write down the values of x for which log to the base of 3 of x is trapped between 0 and 1. So now, we are no longer looking at this function. We are looking at the log, the inverse function of this. We are looking at now this one. And they are saying the y values, so they are indeed saying the y values of the inverse should be between what? 0 and 1. The y values of the inverse should be between 0 and 1. But they are looking for the values of x where that would actually be true. So we need to then use these boundaries as the critical values to determine the value of x when y is equals to 0, and also to determine the value of x when y is equals to 1. Then we'll be in a better position of being able to see those x values when the values of y are between 0 and 1. So my advice would be, I will draw the inverse first, and then I will locate the critical values. So let us draw the graph of the inverse. That is the first approach that we are going to take. And then from there, after drawing the graph of the inverse, you can see now that when x is equals to 0, y is equals to 1. So we have worked out that when x is equals to 0, y is equals to 1. And then now, when x is equals to 3, y, so here we have a point when x is equals to 1, y is equals to 0. That's the point. And then the other point when when y is equals to 1, we get that x is equals to 3. So we are now checking the y values, where the y values are between 0, that is the y equals to 0, and y equals to 1, that is y equals to 1. So we want a portion of the graph where the y values are between 0 and 1. So this is the portion of the inverse. Why am I taking the inverse? Because I'm given the equation of the inverse there. They did not write g is trapped between 0 and 1, but they wrote the log to the base 3 of x is trapped between 0 and 1. So this is the portion that I'm looking for, and the values of x in that portion are 1 and 3. So we expect that x should be trapped between 1 and 3, like that. Let's just check that. Let's verify that one. Indeed, x is trapped between 1 and 3, because they said the y values should be between 0 and 1. So you should check the corresponding x values as the critical values, and then go to the inverse function and try to locate that region. Right. We move on now. We move on to differential calculus. We move on to revising concepts of calculus. We are not going to do everything in calculus. Remember, there was a lesson that we had, I think it should be last week, where we're looking at the basic principles of calculus, the definition first principles. We looked at the rules of differentiation, and then we looked at the sketching of a cubic function. So you can always go back to Pocket School and revisit last week's lesson as the first part of calculus. Now we are going to do the second part, where we are now revising the graph of a cubic function. That would be the interpretation thereof, not the sketching. And then from there, we are going to be looking at the concepts of optimization or applications of calculus. Now, let's look at the graph of a cubic function. The cubic function, obviously, is given in the form ax squared plus bx plus c. And the cubic function can have up to 2 stationary points. That is the maximum number of stationary points that it should have. Remember, it has the possibility of having 1 stationary point or 0 stationary points. That is the possibility. It has a possibility of having a maximum of 2, 1 or no stationary point. Remember, you should not always think a cubic function would have two stationary points. At most, it can have two, but it can also have less than two. It can have between 0 and 2 points of intersection, stationary points. It does not mean that it is no longer a cubic function. This is also cubic. This one is also cubic. It's not only this one, it's not only the first one that is cubic. All three of them are cubic. The difference is that one has two stationary points, the other has one stationary point, and then the last one has no stationary point, but it is still a cubic function. Right. We move on to this now. Obviously, with a shape a is less than 0, you still get the same thing. It's just that now this function is going to start by decreasing, and then from there it increases as well as decreases. Remember, when a is greater than 0, it starts by increasing, it decreases, and then it increases again. You can see here, increases and then decreases and then increases again. So we have the point of inflection there where the concavity changes. So this one starts by decreasing and increases and then decreases if a is less than 0. We can have two stationary points, one or no stationary point. So that is very, very important there. Right. What is the method to sketch? Obviously, the first thing that you need to do, I would always advise you, when you are asked to sketch a cubic function, start with the coordinates of the stationary point, because you get to see whether you have a shape that encompasses two stationary points, or you have a shape that encompasses one stationary point, or you have a shape that encompasses 0 stationary point. So the point of a reference, or rather the point of departure, would be first determine, if the question was not scaffolded, you are just given an equation, you are asked to sketch a cubic function. First determine the coordinates of the stationary point to check which shape out of the three would be the actual shape of your cubic function. Right. And then consider the sign of A and determine the general shape of the graph by looking at the number of stationary points that you got. X and Y intercept by letting Y to be 0 and X to be 0. Remember, there you can, when you want to find the X intercept, you can use your synthetic division method, you can use your long division method, or you can use the inspection method. Now, if asked to determine the coordinates of the point of inflection, you will use the second derivative. F double prime of x is equals to 0, gives you the x value of the point of intersection, and then you can plot the points and draw a smooth curve. Right, now, let's look at the example now of the interpretation. Now, the graph of x cubed minus 4x squared minus 11x plus 30 is drawn below. A and B are the turning points of the graph of f. Determine the coordinates of D, E, and F. D, E, and F. Those are the x-intercepts. So, D, E, and F are the x-intercepts. These three are the x-intercepts. How do you get the x-intercept? You equate y to be 0. Good people, I think this is basic. You just did calculus now. So I want you to just determine these values for me. I'm going to give you just a good 3 minutes. I think you should be done 3 minutes. Just quickly work out for me the coordinates of D, E, and F by determining the x-intercept of that. Your 3 minutes time starts now. Welcome back. Good people, we've just started our calculus. I hope that you were able to work out this basic question. Should not be that complex to do. Should not be that complex to do. Now let's check what we're supposed to do there. We use inspection to find the factor, so I am going to be actually looking at the factors of 30. And then from there, I am going to check which ones are going to give me 0. So by inspection, if I try x equals 2, I get that x equals 2, which means that x minus 2 equals to 0 is a factor. So since this is my factor, I can now use long division, inspection, or I can use my synthetic division. Now, if you check here, I reverted to using a synthetic division to determine the factors. By synthetic division, you can see that if I start here with 2, which is my factor, and then from there, the first value would always be 0. 1 plus 0 gives me 1. 1 times 2 gives me 2. And then negative 4 plus 2 gives me negative 2. Negative 2 times 2 gives me negative 4. Negative 11 minus 4, that gives me negative 15. Negative 15 times 2, that gives me negative 30. Positive 30 minus 30, that gives me 0. So you'll always know it's correct when the last terms there, they simplify or they add to 0. So now I know my A value, my B value, and my C value. So I know that this is x squared, this is x, and that's 15 there. So I can obviously say, okay, I have my factor x minus 2, and then from the synthetic division, I have x squared minus 2x minus 15 equals to 0. So now if I factorize x squared plus or minus 2x minus 15, I'll get the factors x plus 3 and x minus 5. So after getting those factors, I can then say x equals 2, x equals negative 3, or x equals 5. So I will then be able to trace them on the graph. You can see that the biggest value is x at f. That is why I took 5 and assigned it to x at f. And then from there, x at E is also positive. That is why I took 2 and assigned it to x at E. And then x at D is the only negative root. So that is why I assigned the negative 3 with x at D. I hope that you were able to work that out. So that is just the x-intercepts. Now, let's look at the next question. They want us to determine the coordinates of A and B. Let's look at A and B on the graph. You can see that these are the turning points. We have the maxima here, and then we have the minima here. We have the maximum turning point and the minimum turning point. So points A and B are the turning points of F. How do you determine the turning point? You find the first derivative, you equate it to 0, you solve for x, substitute back the corresponding values, or substitute back to the original equation to get the corresponding values of y. Again, I repeat, we are looking for A and B, which are the turning points, the maxima and the minima. So in order to do that, we need to differentiate first derivative of the original function. We equate it to 0. We solve for x. Why are we equating it to 0? Because the gradient at the maxima and the minima, the gradient is 0. And if you find the first derivative, you are determining what we call the gradient function. So now, after differentiating and equating to 0, you solve for x. You are going to get at most 2 values of x, at most. After determining those 2 values of x, you are going to substitute them back into the original function to get the corresponding values of y. Right, let's look at how that can be done. Determine the x-coordinates of the stationary point by putting the derivative to be equals to 0. Let's see that one. You see, this is the original function. We determined the first derivative. If you look at x cubed, to differentiate it, we get 3x squared. Minus 4x squared, to differentiate it, we get negative 8x. Minus 11x, to differentiate it, we get negative 11. We equate to 0 because the gradient at the stationary point is 0. Now, from there, we can then find the factors of the quadratic equation. And then we get that x is equals to 11 over 3 or x is equals to negative 1. Now we check. This one is negative and this one is positive. That is why we aligned this one with negative 1 and this one with 11 over 3. So we said the positive one is x at B, the negative one is x at A. Now that you've determined the roots, the x values, you can then go back and substitute them into the original equation. Let's see. Then substitute the x values into the original equation to determine the corresponding y values. Now let's see the first one. When we substitute 11 over 3, where we see x on the original function, we replace x with 11 over 3, and then we get that this is negative 400 over 27. So we conclude that y at B would be, when x is 11 over 3, y is negative 400 over 27, like that. Now that we've substituted the first one, we need to substitute the second one. Now let's check the solution coming up. So we put f of negative 1. If we substitute negative 1 on the original equation, which means where we see x, we put negative 1, we get 36. So we see that here when x is negative 1, y is 36. So we determined the coordinates of the turning points A and B. So that's how you were supposed to work those out. Hope you are still okay with that. Now, the next question, determine the x-coordinates of the point of inflection of F. The coordinates of the point of inflection of F. Already you have this as negative 1, and then this one, we worked it out as 11 over 3. So this one is 11 over 3. So to determine the point of inflection, you can either, method A, you can either determine f double prime of x is equals to 0 and solve. Find the second derivative, equate it to 0 and solve for x. Or the second method that you can use, you can take the x value of the turning points. So because the point of inflection is the midpoint, between the stationary points. So you can take that as x at A plus x at B divided by 2. You can take these stationary points, add them and divide by 2. Now let's look at how that is done. Method A, using the second derivative. You work out the first derivative, you work out the second derivative. After the first, we differentiate 3x squared. When we differentiate 3x squared, we get 6x. Right? When we differentiate negative 8x, we get negative 8. When we differentiate negative 11, we get 0. We equate that to 0. We simplify, we get that x is 4 over 3. That is the x value of the point of inflection. Alternatively, we can use the midpoint of the stationary points, just like I indicated. So we are going to take x at A plus x at B divided by 2. X at A is negative 1, x at B is 11 over 3, divided by 2. Then this gives us x is equals to 4 over 3. So that is how you can find the x value of the stationary point. The main reason why, good people, I'm subjecting you to both these methods is that sometimes when you are given the derivative of a cubic function, you are not given its equation. They are just telling you that this graph, they draw a graph, they give you the x values or the x-intercept of that graph. They say this is the derivative function. And then they say for which values of x will this have a point of inflection. So you cannot use the second derivative there because you are not given the equation of the cubic function. So you have to revert to method B, where you add the x values of the stationary point and you divide by 2, because the point of inflection is the midpoint between the x values of the stationary points, right? Now, determining the equation of a cubic function, we are going to subject you to 3 cases where you can determine the equation of a cubic function. Case 1, you are given 3 x-intercept, like x1, x2, and x3. If you are given 3 x-intercept, what you do is you use this triple intercept form to say x minus x1, x minus x2, and x minus x3, where x1, x2, and x3 are the x-intercept of the cubic function. So if you are given the x-intercept, you substitute them there, and then you'll be given an additional point. You substitute the additional point x and y to find the value of a. After finding the value of a, then you can multiply inside and simplify to write down the cubic form, the cubic equation in the form y is equals to ax cubed plus bx squared plus cx plus d. So that is the first case. Case 2, you are given 2 x-intercept, x1 and x2, where one of the x-intercept is also a stationary point, and you are given the additional point on the graph. So this is the picture that you are given. You can see that this is an x-intercept as well as the stationary point, so it plays a dual role. So if you are given that, then you should be using this one, because that is a repeated factor, that one, because it acts as both at the x-intercept and also a stationary point. So you are going to use a x minus x1 squared, x minus x2, where x1 and x2 represent those x-intercept, and then you will substitute a point, additional point on the graph to actually be able to determine the value of a. After determining the value of a, then you can use your distributive property, distributive law, to simplify and write it in that standard form there. Right, case 3. Now you are given both the stationary point, or one stationary point and another point on the graph. Now if you are given the stationary points, to determine the equation of the cubic function, use the fact that at the stationary point, the derivative is equals to 0. And then you are going to form equations, and then you are going to solve those equations simultaneously. Now, there is an important here. There's an important thing to note. Please also note that the stationary points play a dual role. If I have my stationary points here, this is the point that lies on what? That lies on f prime of x is equals to what? 0. Because at the stationary point, the derivative is equals to 0. So this can give you equation 1, equation 2. But also remember that the stationary point is also a point on a cubic function. So it can be substituted on f of x is equals to ax cubed plus bx squared plus cx plus d. So it is both a point on f prime of x is equals to 0 and also a point on f. So it can give you 4 equations. Just these 2 points can give you at most 4 equations. So you need to then, so because it plays a dual role, it is also a point where the gradient is equals to 0 and also a point on the graph of f of x. So it can be substituted in the function equation and also in the f prime of x equals to 0 equation. So that is very important to note. Right. Now let us look at the application. Remember, we looked at case 1, case 2, and case 3. Let us look at how we can apply those 3 cases in solving problems. Now, look at the first one. The graph of f cuts the x-axis at x is -2, x is 1, and x is 3. The turning points of f are A and B. PQ is perpendicular to the x-axis with P on f and q on g. F of x is x cubed plus bx squared plus cx plus d. G of x is 2x. Prove that the equation of f is given by. Now you can see you are given x1, x2, and x3. Because you are given those, it means that you are going to use the case 1 approach. Let's check now. Now, if you check, we've used f of x is equals to a into x minus x1, x minus x2, x minus x3. If you check, I've substituted x1, x2, and x3. That's the first thing that we did. And then we are given an additional point on the graph. This is a point 0 and 6, the y-intercept. So we substituted where we see y, we put 6. Where we see x, we put 0. We solve for a. We simply solve for a. After solving for a, we come back to this. We substitute a value. We substitute x1, x2, and x3. And then we are able to then multiply using the distributive property. So if you check, I first multiplied here. X squared minus 3x minus x, which gives me minus 4x, plus 3, which gives me plus 3 there. Then I can distribute the x cubed minus 4x squared plus 3x plus 2x squared minus 8x plus 6, I mean. So I get this, which can simplify to that. Now, if you look at the two, when you compare them, you can see that we actually managed to prove what they wanted us to prove there. Right, we are moving on. Look at this one. This one, the turning point is also the x-intercept, and we have another x-intercept. So we are given two x-intercepts and a point. So we are, in this one, going to be using a into x minus x1 all squared, x minus x2. We are using now case 2 approach. Now they say show that a is 2, b is negative 2, c is negative 10, and d is negative 6. So let's look at what we are going to do there. Obviously, I told you the form. This is the form. Now we substitute the repeated point, negative 1, we get plus 1, and then we substitute 3 there. And then from there, obviously, we look at an additional point. You can see the additional point is d, where x is 0, y is negative 6. Y is negative 6, x is 0. We solve for a, and then after solving for a, then we multiply throughout so that we end up with the equation f of x is 2x cubed minus 2x squared minus 10x minus 6. So we can be able to write down the value of a is 2, the value of b is negative 2, the value of c is negative 10, and the value of d is negative 6. So that is case 2 approach of finding the equation of a cubic function. Let's look at case 3 now, which is the last case. Determining the equation of a cubic function. Now, if we look at case 3, you can see we are given the turning points. We are given the turning points. The function f of x is negative 2x cubed plus ax squared plus bx plus c is sketched below. The turning points of the graph are t and s. Show that a is 21, b is negative 60, c is 47, that is for 7 marks. Now, if we look at this, we can see that already one of the parameter has been worked out, right? So we need these 3. Now, I said to you, if you are given the turning points, you need to first determine the equations by using f prime of x is equals to 0 for this point and for that point. You can get 2 equations from there. And then you can also substitute back to f of x. Substitute these points back to f of x. If you do that, then you can get a further 2 equations. And then you can see how to solve from there. But obviously, at all times, the question itself, as you work it out, it will lead you to all the solutions that you need there. So let's check the approach for this one. If you check first things first, I'm using the first derivative. I've differentiated the original expression. I worked out that the derivative is minus 6x squared plus 2ax plus b. And then from there, I substituted the first stationary point, x is equals to 2. I got equation 1. Just like I indicated. F prime of x is equals to 0. I substitute 2, I get equation 1. I can still apply the same. F prime of x is equals to 0. I substitute 5 to get equation 2. Let's see. Indeed, I'm now substituting 5 on the gradient function. Obviously, we know that f prime of x is equals to what? Is equals to 0 at the stationary points. That's why we are solving f prime of x is equals to 0. If I simplify that, I get equation 2, just like I indicated. Now I can be left with equation 3 and equation 4. However, if I look at equation 1 and equation 2, I can see that I have two equations with two unknowns. The unknown here is b and a. The unknown here is b and a. If the number of equations and the number of unknowns are exactly the same, it means that the two equations can be solved simultaneously to get the values of the unknown. So I can now, because I have two equations with two unknowns, solve the two equations simultaneously. That would give me the value of a and the value of b. Let's see. Indeed, I've solved the two by equating b and b. So I get that a is 21 and b is negative 60. Because I'm solving two equations and I have two unknowns. So I am actually equating 1 or 2, or substituting 2 into 1 is the same thing. So I get that a is 21 and b is negative 60. I'm now left with the value of c. Now I can take any of these points and substitute them back into f of x, because those are dual points. There are points on f prime of x is 0 and points on f of x. So if I substitute 5, I took this one. If I substitute 5 in the original equation, I get that f of 5, which is 18, 2 into 5, where I see x, I put 5, but I've already infused the values of a and b. So I get that c is 43, like that. So I was able to work out the value of a, b, and c. Remember, in this form, you are going to be using the derivative. So you use the derivative as well as you use the original function, because the stationary points are where the derivative is equals to 0. That is why when you are having an equation and you want to determine the coordinates of the stationary points, you determine the derivative and you equate it to 0. So in as much as you can go forward and determine the stationary points, if the stationary points are given, you can still go back and determine the original parameters that were used for those stationary points. So remember, when you determine the stationary points, what do you do when given the equation? You find the derivative, you equate it to 0, you find the two values of the stationary points, and then you substitute them back into the original equation to determine the y values. So same thing here that I did. I determined the derivative, equated it to 0, substituted the two stationary points that I got to get equation 1 and equation 2, and then from there, to get the last value, I took back the x value of one of the stationary points back to the original equation. It gave me the value of c. So it's the same thing. If you can go forward, you can always go back. Just familiarize yourself with movement forward, movement backwards. If you can sketch functions, you should be able to interpret functions, right? Now, let us look at the graph of the derivative of a cubic function. Very, very important. We can find the first derivative. If you find the first derivative of this cubic function, you can see it's a parabolic function. Always the first derivative of a cubic function gives you a parabola. Now, what are the key takeaways that we can take here, or the conclusions that we can make? The stationary point becomes what? The x-intercept. of the first derivative. Very, very important. The point of inflection becomes the stationary point of the derivative function. Very, very important. That is the most important thing when it comes to the interpretation of derivative functions. Let's check also this one to check whether it's the same, what you call the same fact will hold also here. Look, the stationary point became what? The x-intercept of the derivative function. The stationary point of the original function becomes the x-intercept of the derivative function. The point of inflection becomes what? The stationary point. So we can conclude that f prime of x has x-intercept where f has stationary points. F prime of x has a stationary point where f had point of inflection. That is the most important takeaway for interpreting the graphs of the cubic function, or the graphs of the derivative of a cubic function. Now let us look at the application problem. The sketch below is given the graph of, in the sketch below, the graph of y is equals to ax squared plus bx plus c represents the first derivative of the function of f, where f is a cubic function. Now you can see they said write down the x coordinate of the stationary point. It takes us back to this. If you understand here that the stationary points of the cubic function become the x-intercept of the derivative function, the point of inflection of the cubic function becomes the stationary point. If you can understand that, then it should be easy to respond to this question. State whether each of the stationary point is a local maximum or a local minimum. So that's where we have to use our first derivative test or the second derivative test. Now, determine the x-coordinates of the point of inflection. You see, I said to you, when we were calculating the point of inflection of that first example, I said, let me use two methods, because there comes a time where you are given the derivative function and you are not given the equation of that function, but you are given the roots there of that function. So you should be in a position of being able to calculate, right? Hence or otherwise draw the graph of f. Now let us look at those questions, the solutions thereof. The x-coordinates of the stationary points. Remember we said the x-intercept of the derivative function give us what? The x-coordinates of the stationary points of the cubic function. So x is equals to 1, it's this one, or x is equals to 2. So these are the what you call, these are our stationary points on the cubic function. They become the x-intercept of the derivative function. Now determine the x-coordinate of the point of inflection. I said to you, if you are given the stationary points, then the point of inflection becomes the midpoint of those stationary points. So we are looking for this point. It is the midpoint of these two. So x would be equals to the first value 1 plus 2 divided by 2. So this becomes 3 over 2. So that is the x coordinate of the stationary point of the original function. But here it is the axis of symmetry of the derivative function. Right. State whether each of the points is a local minimum or the local maximum. We are going to use the first derivative test to do that. So we are going to check, if you look at this point, x is equals to 1, we are going to check whether the gradient is positive or negative there. So we are going to check for x less than 1. If you check here, this is the gradient function, so the gradient is positive. So we are going to say when x is less than 1, when x is less than 1, the gradient f prime of x is positive. But when x is trapped between 1 and 2, when x is trapped between 1 and 2, what happens to the gradient? F prime of x is negative. So what do you see now? For x equals 1, you can see that when x is equals to 1, f prime of x is equals to 0. So you can see that less than 1, the graph is decreasing. At 1, the graph is stationary. Between 1 and 2, the graph is increasing. So you can see that now this represents a local minimum. That is the first derivative test. Now, if we look at x is equals to 2, we know x is equals to, when x is equals to 2, f prime of x is equals to 0. The gradient is 0 when x is 2. But between 1 and 2, what do you see? The gradient is negative between 1 and 2. At 2, I made a mistake here. When x is less than 1, we can see that the graph is increasing because we said the gradient is positive. When x is equals to 1, it is stationary. When x is trapped between 1 and 2, it is decreasing. So you can see that f prime of x is positive here, f prime of x is 0 here, f prime of x is negative there. What does that mean? You start by increasing, you are stationary, then you decrease, which means that you have what we call a local maximum. Now, if we investigate for x is equals to 2, you can see when x is trapped between 1 and 2, you can see that when x is trapped between 1 and 2, the gradient is negative. But when x is equals to 2, the gradient is 0. But when x is greater than 2, this side, you can see that the graph is above the x-axis. The gradient is positive. So you can see that it starts by decreasing, stationary, and then increases. So you can see that now this becomes what? A local minimum, like that. So we were able to state whether each stationary point is a local min or a local max. Let's check now. That is the formalized version of the first derivative test. When x is less than 1, what do you see? F prime of x is positive, so f is increasing. It starts by increasing. When x is trapped between 1 and 2, we get that the gradient is negative, so x is decreasing. So it increased stationary, then decreased, so x is 1, is a local maximum. But when x is greater than 2, the gradient is positive, x is increasing. That means that x is equals to 2 is a local minimum. That is how you can use your first derivative test. Now, the last one, hence or otherwise sketch the graph of f. That is the original cubic function. Now, we've already determined that this is a local max and this one is a local minimum by using the first derivative test. So we can simply draw our cubic function. X is equals to 1 is a local maximum, and then x is equals to 2 is a local minimum. We are done because they are interested in what? In the rough sketch, the shape as well as the stationary points there. Right, good people, we are now going to conclude our lesson. The last part of the lesson will be on optimization. Because of time, we are just going to look at a few questions on optimization. Fine. Now, we are now looking at application of calculus, which is divided into 4 different sections. Application to shapes, application to graphs, rates of change, and calculus of motion. I think for this particular lesson, because of time, we are only going to look at application to shapes and application to graphs. Now, let's check this out. These are the 4 categories as I indicated. Let's look at the first example. That is a word problem. The difference between 2 digits is 900. Determine the 2 integers, or the difference between 2 integers is 900. So if the first integer is x and the other one is y, the difference between x and y is 900. Determine the 2 integers which will determine the smallest product. You want the product. The product would be when you multiply them. So let's see. Formulating an objective function. How do we do that? Let x denote the first integer and y denote the second integer, and p denote the product. So x minus y is 900 because they said the difference gives you 900. If we make y the subject, we get that x is equals to, or y is equals to x minus 900. The product obviously is when we multiply the 2x times y. So the product in terms of x, when we see y, we put x minus 900, and then we get that the objective function, which is the product, is x squared minus 900, and we want the smallest product. So we are going to differentiate the objective function for the product and equate to 0 to find the value of x. Optimizing and determining integers. You see, we differentiated the objective function, and then from there, what do? We equate to 0 f prime of x, not t, and then from there we get that x would be equals to 450, and then from there, if we substitute back the 450 into the y parametric equation here, we get that y would be negative 450. So those are the two products there. So that was not a difficult problem. Now we have another one. A rectangular area is to be enclosed on 3 sides by a fence and an existing hedge, which forms the 4th side. 200 meters of fencing is available. Show that y is equals to 200 minus 2x. Now, this is an existing side. So when we fence, we only need 1, 2, 3 sides. So it means we have x plus y, and then we have 200 meters of fencing is 200, because that is the perimeter that we need to fence. And then we have that this is 2x plus y is equals to 200, which means y is equals to 200 minus 2x, like that. So we did the first one. Determine the largest possible area of the rectangle. Now, what would be the area of the rectangle? Is length multiplied by breadth. So area is x times y. Since we've expressed y in terms of x, we can write down the area as a function of x alone. So a of x would be x into 200 minus 2x. So this would be 200x minus 2x squared. That is the objective function. So determine the largest possible area. So to maximize the area, we find the derivative f prime of x. When we differentiate that, we get 200 minus 4x when we differentiate that. But for max area, a primes of x should be equals to 0, which means that we would have 0 is equals to 200 minus 4x. So 4x is equals to 200. If we divide that, x would be equals to 50. And then if you are to substitute back, you will have that now the maximum area, where you see x, you're going to put 50. A's of 50 would be 200 into 50 minus 2 into 50 squared. You'll calculate that for me using your calculators to be able to work out the maximum area. What did we do here? We said there's an existing hedge there, which means we are to fence the remaining 3 sides. So the remaining 3 sides are x, x, and y. We are given 200 meters of fencing to use. So we are going to add all 3 and get 200. So we can write y in terms of x, which allows us to formulate an objective function for the area in terms of x only. And then to maximize, we differentiate, we equate to 0, and then we solve for x. That is the value of x is the value where we get the maximum area. Then we substitute back to determine that maximum area. You will substitute this in your calculators and get the answers for me. Right, another example, application to graphs. This is a very interesting example. I like this example. So I want to conscientize you on a few things that you need to look at in this particular example. Determine, we are given f of x is x squared. If I can draw that graph, f of x is x squared. So this is x, this is y. And then determine the minimum distance between the point. We are given a point somewhere there. That is the point 10 and 2. We want the minimum distance between the graph and that point. So that is the distance that we are looking for. We want to minimize that distance. So it means we have to use the distance formula. But for us to use the distance formula, we need the coordinate. We already have the coordinate of that point. We need the coordinate on the graph. We know the coordinate would be x. It would be x and y. Any point on the graph of f will have coordinates x and y. But because x can be written in terms, y can be written in terms of x, y is equals to x squared. We are going to replace y with x squared. So we have a point x and x squared. So we have a point x and x squared here. We are going to find the distance in terms of x. Let's check how that can be done. Any point on the graph f on and y is where y is x squared is given as x maps x squared. Now the distance, I'm taking the distance now from the point to the point 10 and 2. So this is how I determine that distance. Simplifying that, I get that the distance is x squared minus 20x plus 100 plus x to the index of 4 minus 4x squared plus 4. Now, that would be the distance in simplified form. Now, the problem with this is, in order for me to maximize this thing, I need to differentiate. But now, I cannot be able to differentiate if it is everything is underneath the square root. I do not have the tools. In grade 12, you do not have the tools to directly differentiate something that is underneath the square root. You can only do that when you get to tertiary, when you use the chain rule. But for now, you don't know how to differentiate something that is underneath the square root. So we need to use other properties to be able to find the maximum distance. We will use the properties of the sets to say if this expression is underneath the radical, if what is underneath, if this thing that is underneath the root is a maximum, then the whole thing becomes a maximum. So if I've worked out the expression and it gave me the maximum of 16, if I've worked out the expression gave me the maximum of 16. If I put that under the square root, because everything is subjected to the square root, the maximum will then be 4. So the maximum occurs when whatever that is underneath the square root is also a maximum. So I'm going to take what is underneath the square root and maximize it. So that is why I will only differentiate the expression underneath the square root. If I differentiate it and set it to be equals to 0, I get that 4x cubed minus 6x minus 20 is equals to 0. If I solve for that, it's a cubic equation, which means I have to find a factor and use my synthetic division or whatever method. So I found these are the factors of that. Now I've worked out that this one, if you check this one, the discriminant here is less than 0. So the roots here are non-real roots for this expression. So the final value is x is equals to 2, which means I can substitute it back and get that the maximum distance is 8,25. Remember, good people, the most important takeaway here was that if everything is underneath the square root, you cannot directly differentiate it. So the most important thing for you to do is you use those laws of sets to say if everything underneath the square root is maximized, if the expression underneath the square root is maximized, then everything else becomes maximized, right? Good people, obviously because of time, we cannot be able to actually touch on everything that is here, but I believe that with everything that we've just done here, you should be able to respond positively to questions that are going to be posed to you tomorrow. Remember, good people, practice, practice, and practice. You have the potential to do well in paper 1. Please practice all the topics. Remember the grade 11 topics on finance and probability. Practice them as well. They will be in an exam paper tomorrow. We wish you all the best. Please take care of yourselves, take care of each other, and practice mathematics. Goodbye.